In this video, let's talk about products and quotients of complex numbers in polar form. To do so, we are going to consider two complex numbers. The first one, two complex numbers in polar form. The first one, z1 equals, let's say r1 into cos of theta 1 plus I sine of theta 1. And the second complex number, z2 in polar form, was r2 into cos of theta 2 plus I sine of theta 2. Now, before we start multiplying and dividing these complex numbers, let's recall some trig identities. First, sine of A plus B. We know that this is the same as sine of A cos of B plus sine of B cos of A. And sine of A minus B is the same as sine of A cos of B minus sine of B cos of A. The next identity is cos of A plus B. This is the same as cos of A cos of B minus sine of A sine of B. And last, cos of A minus B is the same as cos of A cos of B minus sine of A sine plus sine of A sine of B. Now we are going to be using these identities subsequently. Now let's go back to our complex numbers. Let us consider the product of the complex numbers z1 and z2. z1 times z2 should be equal to r1 r2 in bracket cos of theta 1 plus I sine of theta 1, all of this into cos of theta 2 plus I sine of theta 2. There, that is what we should get. Now we are going to simplify by expanding the brackets. So the first term is cos of theta multiplied by the first term in the second bracket. So this is going to give us something like this: r1 into r2, all of this into cos of theta 1 times cos of theta 2. And then this term multiplied by this term. So we have plus I sine of theta 2 times cos of theta 1. And this term multiplied by this term, we have plus I sine of theta 1 cos of theta 2. And then we have this term multiplied by this term, we have plus I squared sine of theta 1 sine of theta 2. There you go. Now we are going to group like terms. So this is going to give us r1 times r2, all of these into, so bringing like terms together, we know that I squared is -1. So this is going to be cos of theta 1 cos of theta 2 minus sine of theta 1 sine of theta 2. All of this plus this term and this term, we have I sine of theta 2 cos of theta 1 plus I sine of theta 1 cos of theta 2, and close the bracket like that. Now what do we get? To continue, we have R1 times R2 into this will simplify to cos of theta 1 plus cos of theta 2, close the bracket. And this, all of this should simplify to plus I sine of theta into theta 1 plus theta 2, and close the bracket. So for two complex numbers z1 and z2, the product of z1 and z2 can be expressed as r1 times r2, all of this into cos of theta 1 plus theta 2, all plus I sine of theta 1 plus theta 2, and close the bracket. So that is the product of two complex numbers. Now let's consider the quotient. The quotient z1 and z2. So here we will have z1 over z2 equals r1 into cos of theta 1 plus I sine of theta 1, all of this over r2 into cos of theta 2 plus I sine of theta 2. Now we need to simplify this by realizing the denominator. And to realize the denominator, we need to multiply the numerator and denominator by the conjugate of the denominator. And remember how to multiply a complex number by its conjugates easily. Let's say we have a complex number a plus bi. Its conjugate must be a minus bi. And when we multiply these two complex numbers, we simply get a squared plus b squared. That is the result of the product of a complex number by its conjugate. So here we have to multiply this and this by the conjugate of the denominator. So this is going to give us r1 into cos of theta 1 plus I sine of theta 1, all of this into the conjugate of the denominator, which is cos of theta 2 minus I sine of theta 2. All of this over, we do the same thing with the denominator. So we have r2 into cos of theta 2 plus I sine of theta 2. All of this into cos of theta 2 minus I sine of theta 2. Close the brackets. Now we have to simplify. Now simplify by expanding the brackets. So we write this is equal to r1 into So this term multiplied by this term, we get cos of theta 1, cos of theta 2. This term multiplied by this term, we have minus I sine of theta 2 cos of theta 1. And this term multiplied by this term, we have plus I sine of theta 1 times cos of theta 2. And then this term multiplied by this term, we have minus I squared sine of theta 1 sine of theta 2. Close the bracket. All of this over R2 into, so multiply the conjugate, we have cos squared of theta 2 plus sine squared of theta 2. Now we have to recall cos squared theta plus sine squared theta must be 1. So now bringing like terms together, simplifying the numerator by bringing like terms together, we have R1 into cos of theta 1 cos of theta 2. I squared is negative 1. Negative and negative should be positive. So this becomes plus sine of theta 1 sine of theta 2 plus, so I'll write this term first, I sine of theta 1 cos of theta 2 minus I sine of theta 2 times cos of theta 1. All of this divided by R2 multiplied by 1, since cos squared theta 2 plus sine squared theta 2 should be 1. Now, when we simplify, we should get this. R1 over R2 into cos theta 1 cos theta 2 plus sine theta 1 sine theta 2 should be cos of theta 1 minus theta 2 plus I. So the common factor is I. We factor out I, and then we have sine in bracket theta 1 minus theta 2. So therefore, for the quotient of two complex numbers in polar form, z1 over z2, this is equal to r1 over r2 into cos of theta 1 minus theta 2 plus I sine into theta 1 minus theta 2, like that. Okay, that is it for product and quotient of two complex numbers, z1 and z2, in their polar forms. Now, we are going to take some examples. Write down the moduli. Moduli is a plural form of modulus, and arguments of negative root 3 plus I and 4 plus 4I, hence expressed in the form R into cos theta plus I sin theta. The complex numbers in bracket negative root 3 plus I all into 4 plus 4i, and in bracket negative root 3 plus I all over 4 plus 4i. So that is example number 1. Now let's begin with the solution. Let's start by writing the moduli of the two complex numbers. So the first one, the modulus of negative root 3 plus I, we know this is the square root of negative root 3 squared plus 1 squared. Since for a complex number, the modulus of a complex number a plus bi is just equal to a squared plus b squared. So this is going to be square root of 3 plus 1. 3 plus 1 is 4, so we have square root of 4. So the modulus is equal to 2. So let's call this R1. And then the second complex number is supposed to be 4 plus 4i. So the modulus of 4 plus 4i is equal to the square root of 4 squared plus 4 squared. And this should be square root of 16 plus 16. 16 plus 16 is 32. So this is square root of 32. And 32 is the same as square root of 16 times 2, which can be written as square root of 16 times square root of 2. Square root of 16 times square root of 16 is 4. So this is 4 root 2. So let's call this R2. So we say R2 is equal to 4 root 2. Now that we have written the moduli of the two complex numbers, let's go and write down the arguments. Let's begin with the first one. We want to write the argument or the principal argument of negative root 3 plus I. Now remember, to do so is always important to represent the complex number on our Argand diagram so we can actually see the correct quadrant. So this is my y-axis and the x-axis. Now the real part is negative 3. Negative 3 should be in the second quadrant. The imaginary part is positive. So this is it right here. So this must be in the second quadrant. In the second quadrant, the value of theta must be obtuse and positive. So this is the angle theta. Here we are going to consider an associated angle alpha. So this is square root of 3 and this is 1. So we are going to consider our tan ratio. So the tangent of the angle alpha is equal to 1 over square root of 3. Now we know that tan of 30 degrees is equal to 1 over square root of 3. So therefore alpha, which is supposed to be tan inverse of 1 over square root of 3, must be equal to 30 degrees, or we say alpha is equal to pi over 6. Now, what is the value of theta? Theta is supposed to be obtuse. So theta should be pi minus pi over 6. So this is equal to 5 pi over 6. So the first argument is 5 pi over 6. So the argument or the principal argument of negative root 3 plus I is equal to 5 over 6 pi. Now let us find the argument of 4 plus 4i. So the principal argument of 4 plus 4i. So to do so, we have to draw our Argand diagram again. So x, y-axis. Now the real part is 4, so this is on our positive x-axis. The imaginary part is 4i, this is on our positive y-axis. So this must be in the first quadrant. So the angle must be acute. So this is 4 and this is 4. So we can find the angle theta directly. So this is the angle theta right here. So we say tan of the angle theta is equal to 4 over 4. So tan of the angle theta is equal to 1. Now recall that tan of 45 degrees is equal to 1. So it implies the angle theta, which is tan inverse of 1, must be 45 degrees. And 45 degrees is the same as pi over 4. So the argument is pi over 4 because it is in the first quadrant, so it must be acute. Now let's get into the next part of the question. Next part of the question, we have to express the complex number negative root 3 plus I all into 4 plus 4i in the form r into cos theta plus I sine theta. Now, as you can clearly see, this is a product of two complex numbers. So it should look something like negative root 3 plus I all into 4 plus 4i must be equal to, so this is of the form z1 times z2, which is equal to r1 times r2 into cos of theta 1 plus theta 2, all of this plus I sine of theta 1 plus theta 2. So we can say that z1 is negative root 3 plus I, and z2 is 4 plus 4i. So we know that the modulus of z1, so modulus of z1, we got 2, and modulus of z2, we got 4 square root of 2. And the argument of z1, we got 5 pi over 6, 5 pi over 6 plus pi over 4 plus I sine of 5 over 6 pi plus pi over 4. That is what we get. Now we have to add these together. So, and the argument of z2, we got pi over 4. So, therefore, in bracket, negative root 3 plus I all into 4 plus 4i should be equal to the product of the two moduli should be 2 times 4 root 2, all of this into cos in bracket 5 over 6 pi plus pi over 4. The LCM of 6 and 4 should be 12, so this should be, so multiply this by 2, multiply this by 2, we get 10 pi over 12 plus, multiply this by 3 and multiply this by 3, we get 3 pi over 12. So the sum should give us 13 pi over 12. Now, is this the principal argument? Now, let us take a look at this in the Argand diagram. We see that in our Argand diagram, clockwise, since this is positive, so it has to be anti-clockwise, sorry. It is more than, this is more than pi. So it has to be in the third quadrant. So it has to be in the third quadrant. And this is not within range. So since this is more than pi, and we know that the range should be negative pi less than theta less than or equal to pi. So we have to go clockwise. So this should be the angle. So in this case, the angle is going to be obtuse and negative. So the correct value right here should be this angle. So that is going to be 2 pi minus 13 pi over 12. So this is 1. So this is going to be, multiplying this by 12, we have 24 pi over 12 minus 13 pi over 12. So this is going to give us 11 pi over 12. Since this is clockwise, it has to be negative. So the argument must be negative 11 over 12 pi. The product of the two complex numbers, that is negative root 3 plus I into 4 plus 4i. This is equal to the product of the two moduli. 2 times 4 is 8. So that is going to give us 8 root 2 into cos of negative 11 over 12 pi plus I sine of negative 11 over 12 pi. That is the product of the two complex numbers in polar form. Now next, we want to express the quotient of the two complex numbers in polar form. That is negative root 3 plus I all over 4 plus 4i. Now, this is of the form z1 over z2, which is equal to r1 over r2 into cos of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. It implies, in bracket, negative square root of 3 plus I all over 4 plus 4i is equal to, the modulus of the first one is 2, and the modulus of the second one is 4 root 2. All of this into cos of 5 over 6 pi minus pi over 4 plus I sine of 5 over 6 pi minus pi over 4. Now let's go ahead and find the difference between 5 over 6 and 1 over 4. So 5 over 6 pi minus pi over 4. The LCM is 12. So multiply this by 2, multiply this by 2, we have 10 pi over 12. Multiply this by 3, multiply this by 3, we have 3 pi over 12. 10 minus 3 is 7, so the difference is 7 pi over 12. And this is less than pi, so this is within range. So it implies the quotient of negative root 3 plus I and 4 plus 4i is equal to, so 2 divided by 2 is 1, 4 divided by 2 is 2, so we have 1 over 2 square root of 2 into cos of 7 over 12 pi plus I sine of 7 over 12 pi. And we could also simplify this by multiply this by square root of 2, multiply this by square root of 2. So this is going to be square root of 2 over root 2 times root 2 is 2. 2 times 2 is 4. Root 2 over 4 into cos of 7 over 12 pi plus I sine of 7 over 12 pi. So that is the polar form of the quotient of the two complex numbers. So thank you for watching and see you in the next video.